The first speaker today is Teichmuller on the Hausdorff dimension, the set of non-linear ergodic change consideration.
So, first of all, thank you, Antoine, Jonathan, for inviting me to speak. This is joint work with John Chaika. And before I get started, I thought I would say, in our paper we acknowledge, or more to the memory of Bill Veach and Jean-Christophe Foucault's, and so I thought I would, that for their inspiration for us and for many other people, and so I thought I would mention that as a kind of a dedication. Okay, let me say what the theorem is. So we're going to let delta be the standard simplex in our Euclidean D space, so this is a D minus one dimensional space, D minus one dimensional. We have some permutation pi on, so permutation on D letters. And then, so irreducible permutation. For each point in the simplex, and with this fixed permutation pi, you get an interval exchange. So x, this one just write x, and pi determine an interval exchange. IT, let me just draw kind of the standard picture, perhaps, where the permutation is, say this is on D letters, 4 letters. You divide the interval 0 to 1 into, in this case, 4 pieces of length x1, x2, x3, x4. And so you take, for example, the first interval, it goes to the last interval. So what is interval exchange? Takes the first interval to the last interval by a translation. It takes the second interval to the third place. So here's the third place, so this is the second interval. It goes by a translation to the third place, and so forth. So this is the image of I2. And the third interval goes to the third place, goes to the second place, the last interval goes to the first place. Okay, so we're interested in the, so let me remind you what it means to be uniquely ergodic. So say the interval exchange is uniquely ergodic. Well, Lebesgue measure is invariant, and so T is uniquely ergodic if Lebesgue measure is the only invariant probability measure. Lebesgue, which is invariant, is the only invariant measure up to scaling. Now it's the famous theorem of Kronecker and Weil, or Weil really, that when D is 2 or 3, minimality implies unique ergodicity. For D greater than or equal to 4, there were, starting quite some time ago, examples have been constructed by many people over the years of minimal, but not uniquely ergodic, but not uniquely ergodic. So I'm going to write NUE for not uniquely ergodic. So I think the first examples really were due to Veach, and then there were examples, constructions due to Michael Keene, Satayev, many other people, and more recently there have been topological constructions using Thurston's sphere of measured foliations. I think that was initiated by Gabay, and then there are also constructions by Leininger, Rafi, Lemzin, Adami, and so forth, sort of more topological. In this talk, I'm going to be using Rocha induction to construct examples. Okay, so here's the theorem. So let me let NUE of delta equal the set of x's such that t is not uniquely ergodic. Okay, so the issue is how big a set that is, and that's the content of the theorem. So the theorem, again, joint with John, I'm going to assume d greater than or equal to 5. Okay, in a minute we'll about d equal 4. And the permutation pi should be in the Rauzy class of the symmetric permutation. So for the moment, just think of the symmetric permutation. Here's a symmetric permutation on 4 letters. So let's say pi is the symmetric permutation. This is pi 4. But actually, pi is really in the Rauzy class. So I'll explain what that is, although we had to talk about this yesterday. I will repeat. Pi is in the Rauzy class of the symmetric. And the theorem is that the Hausdorff dimension of NUE is, well, the dimension of the simplex is d minus 1, and we lose a half. So it's d minus 1 minus a half. So, so my contribution was to realize that this was d minus 3 halves. Okay, so maybe we shouldn't have done that. Okay. So d equal 4 was previously done by John and J.F. Freya. There, when there are 4 letters, there's only one Rauzy class. Okay, so what's really new here is, well, d greater than or equal to 5. Okay, let me give a corollary. So, as usual, x omega is a translation surface. And let me write NUE of x omega is the set of angles theta in 0 pi or 2 pi, such that the flow in direction theta is not uniquely ergodic. So in our usual picture, we have some octagon or something. The translation surface opposite sides identified. And then we have a 1-parameter family of flows depending on the direction. We're looking at the non-ergodic, non-uniquely ergodic directions. And the statement is, so the corollary is if x omega, let's assume we're talking about the hyperelliptic component of a stratum. So 2g or hyperelliptic component g minus 1, g minus 1. Okay, so there are let's see, 2g minus 2, right? Sorry. We'll look at the hyperelliptic components, and so I want to look at translation surfaces in these hyperelliptic components. The reason is they're the ones that give permutations, like first return maps will be a permutation in the Rauzy class of the symmetric. And the statement is for almost every x in these, almost every translation surface in these components, the set NUE has Hausdorff dimension 1/2. Hausdorff dimension. Now, it can't be true for every surface, because if you take, for example, of each surface, a lattice Teichmuller curve, or of each surface, then the non-uniquely ergodic directions are just the directions of the parabolic transformations, and that's countable. So the Hausdorff dimension is certainly 0. There are examples, or a theorem really, of Smiley and Weiss that say that if you have some cover of a beat surface branched over a single point, so itself is not a beat surface, then the Hausdorff, again, this set is countable. There are examples where the set is uncountable, this non-uniquely, but it still has Hausdorff dimension 0. So this is certainly far from an almost everywhere statement. What I would like to say as a kind of an open problem is the only answers that I know of for any possible Hausdorff dimension are either a half or 0. And possibly interesting question is whether you get any dimensions between 0 and a half, strictly between them. Okay. Let me give, before I talk about Rocha induction, let me give a brief history of this problem. I've sort of been interested in it on and off for quite a long period of time, and so kind of very happy to see this exact answer. But a history, so let me just make it brief. So the fact that the Lebesgue, so the first kind of statements were that the Lebesgue measure of NUE of delta is 0, and then after that came that the Lebesgue measure of NUE of x omega is 0 for all x omega. So here, this is, so Beach and I proved this independently. This result is due to, came a few years after that, due to Steve Kirchhoff, and Smiley and myself. So the measure 0 statements. Then it led to ask, well, what about Hausdorff dimension? And then John and I, Hausdorff, so what we showed was that for each connected component of a stratum, there exists a constant C which is positive, such that for almost every x omega in that component, I'll just call that C, bad letter I guess, the Hausdorff dimension x omega is C. So what this theorem is telling us is that C is a half, or the corollary is saying that C is a half. Yeah, this also allowed for quadratic differentials. Is that what you're asking me? I'm sorry.
There's a number of
Pardon me?
one's case that is
Oh gosh. Okay. Okay, H, that's usual notation. Okay. Yeah, thank you. So for any component of a stratum, H alpha, there was a constant depending on that, where the a priori, where the Hausdorff dimension was that constant. And what this is saying is constant is a half, doesn't depend, well, at least in these hyperelliptic strata. Our guess is that this theorem ought to be true for every permutation, not just this Rocha class of symmetric. The symmetric one was somehow easier to deal with, but it probably should be a half for any permutation. Okay. And then one more history background, or actually two more statements. Then a little bit after this, I showed that the dimension was less than or equal to a half. So the next statement was that the dimension is less than or equal to it. So I got that C was bounded by a half. And so what this, again, what's here is to prove a lower bound of a half. Okay. Now, actually, let me say something. There's a recent theorem of 6 authors, which I want to say what that theorem is, which actually implies this. It's strong. There's a recent theorem that is stronger than this. So I want to talk about just mention a recent theorem. Okay, so there are 6 authors here, and I hope it doesn't take the rest of my time to write down their names. But let me try. So this is a theorem of Paul Pisa. So I'm not writing first names, yes, except for Paul. See, that's 1, 2, 3, that's 5. Oh, and Ershenko. Okay, so here's what they do. They show for, so I need a definition first. You say that, let's again restrict to translation surface. You say that x omega diverges on average if the following holds. So you take the Teichmuller flow, you look at it, for example, in the behavior of the Teichmuller geodesic determined by x omega, and you look at it in, say, the stratum, and you ask, does it diverge? Does it leave every compact set? So that's diverge. On average means, well, on average it leaves every compact set. So here's a definition. If for any compact set K, say in the stratum, you look at the amount of time GT x omega spends up to time, let's say t, it spends in K, and divide by 1 over t, multiply by 1 over t. So that's the average amount of time you spend in K. That goes to 0 as t goes to infinity. So that's the definition of diverging on average. I think another word for this, expression for this, is loss of mass. The geodesic is not recurring very much to a compact part, so mass is being lost. So here's what they prove. You take, let's say again, the set of you take a translation surface, you rotate, look at all possible directions. So you, for example, look at n. Let's see. Here's notation. I'm not sure what they use. Divergence on average, div av of x omega. So this is the set of theta, such that the if you, for example, rotate x omega by theta, that this rotation, that this translation surface diverges on average. Okay, so that's the setup, and their theorem is that the Hausdorff dimension of this set is also at most a half. So, okay, so there's an inclusion of 3 sets here. So why I'm saying it's stronger than this is because this should be NUE, sorry. That the non-uniquely ergodic of x omega is sitting inside the set of directions where you diverge, and then that's sitting in clearly inside the set of directions where you diverge on average. And this set has Hausdorff dimension a half, so certainly this one does, and most a half, sorry. So this one does, and so obviously that does as well. So that's a stronger statement than that.
Is it for every surface?
This is for every surface, yes. Did I not say it? I probably didn't say it. Yeah, this is for all
Genus
x omega.
Genus is 2.
Genus can be 1. Oh, okay. Yeah, I mean, genus is at least. This is still true in genus 1. It's just that this is countable, this is empty. Still true in genus 1. Okay. Okay. All right. Okay. So now I want to start talking about the construction of non-uniquely ergodic. So, as I said, there's been a...
Can I ask a question?
Yes, sure.
If you just wanted to prove the lower bound for dimension average, that's supposed to be easy, right? The lower bound for the Hausdorff dimension.
Yeah, so Paul and I gave a lower bound. So what we proved is that this is exactly a half. So we gave a lower bound also. It's at least, it's greater than or equal to half for all x omega. Whether it's much easier than his upper bound.
No, it's easier than your lower bound for the non-nuclear ergodic. Does it make life easier? You have a lower bound for the non-nuclear ergodic.
Well, this is, okay, so here we only have almost everywhere. And this statement is every. So it's a big difference. It's a big difference. I mean, again, we can't have, you know, there's no every statement possible here because it could be 0, it could be a half. Here, this statement, so you know, again, I didn't emphasize it enough. It's every translation surface, and the lower bound greater than or equal to half is true for every translation surface. Okay? It's even true for tori, because you know, on the modular curve, you can't diverge unless you're going in a rational direction. You can diverge on average if your continued fraction expansion has a certain property. And you can write down what that property is, and it has been, you know, people have shown that the dimension is a half. But the point is it's true for higher genes too. Okay? Okay. So let me talk about, yeah, so as I said, there are lots of methods of proving, trying to construct non-uniquely ergodic interval exchanges, measured foliations. The approach we're taking is, I think, first roughly due to Michael Keene in the 70s with his, is using, I don't think he called it, it wasn't called Rocha induction then, but I think it's, what he did was very similar. So let me talk about Rocha induction. And I want to make some points about it. So, I mean, again, probably familiar to most of you, but you have some permutation, you have some possible length, this is d equal 5, you have some possible lengths of curves, you maybe have an interval which is denoted I sub k, and it goes to this interval is labeled I sub j, and I sub k goes to the end. Okay? So that's where I sub k goes. In our example over there, I would be comparing the first interval to the fourth interval, if that's the permutation.
I'm sorry,
Yeah.
perhaps it's already been said, but so they're always lower bounds, they're always upper bounds, where the lower bounds?
Sorry, here?
Where the one halves.
Okay. So, this is always less than or equal to a half. The theorem here is that it's typically a half. Okay? This is, as it turns out, always exactly 1/2. I only stated the upper bound, but it turns out there is a lower bound also of a half. So this is always a half. Here, I don't, well, all I know is between 0 and a half. Okay. And certainly for almost every x omega, it's a half, because it's half here. Okay? Okay, so what do you do in Rauzy induction? You compare the length of ij to the length of the interval that goes to the last one. So in this picture, ik, in this example, ik is bigger than ij. This is bigger than that. So what we do is you induce on you get rid of the last interval I sub j, and you induce on what's left. So you look at 0, 1 minus ij, and you take the first return. First return to that subinterval. Okay? And the other picture is if I sub k is smaller than I sub j, then you see where I sub k is, it's right here, and then you induce you remove the piece of I sub j that corresponds to the length of I sub k and induce on that. So similar, I just said similar if ik is smaller than ij. If they're equal, Rauzy induction isn't defined. That's a set of measure 0. We don't, in fact, codimension 1, we don't care about those. Okay? Now, the point I want to make, I mean, this is familiar probably to many people. The point I want to make is you are presented with a simplex and a permutation. And if you're building, now we're trying to build non-uniquely ergodic interval exchanges with some property, you now have a choice. You can say, in this simplex, I want I sub j to be bigger than I sub k for some reason, or you want I sub k to be bigger than I sub j for some reason. You want to accomplish something. And so you have a choice. And, well, we're going to make choices over and over and over again to accomplish something. So the picture is, of course, here's a drawing of the simplex, and here is maybe ij bigger than ik, and here's ik bigger than ij, and you can decide you want your interval exchange to live in there or live in here. Okay? Now, along with this, there's a matrix, a very simple matrix, which was discussed yesterday, which is, there's a matrix A, which goes, well, I'm going to renormalize. It goes from the simplex to itself, and it takes, you plug in the new lengths, and the matrix A gives you the old lengths. So you do this interval exchange, you do this Rauzy induction, you get a new interval exchange with a new permutation. It was discussed yesterday what are the possible permutations you get, but you get a new permutation and you get new lengths, and the original lengths are so these will be the original lengths. And these will be the new lengths, and they're related by this very elementary matrix A. And what this matrix does, it takes the standard simplex, and depending which one you're doing, it either maps the simplex to here or maps it to here. Okay? Now, it's this elementary matrix. It has ones on the diagonal and one in one other place, and otherwise 0. But what I want to emphasize about this is what happens if we do this over and over again. So I want to talk about iterating Rauzy induction. So suppose we do this n times. So we get a matrix M sub n. Again, I projectivized the matrices so that everything is, all the interval exchange, so these are really projective matrices. Delta to delta. So the picture is, again, here is the matrix Mn. You've taken the standard simplex, and then you've divided the original simplex into tinier and tinier pieces, and M sub n will map the standard simplex into a tiny piece. Now you do Rocha induction again, so now you are working on that simplex. You have some permutation. You decide who you want to win, either the interval that goes to the last one or the last one, and you get a new matrix. So there's an A here and then a new matrix, Mn plus 1. If we do Rocha induction again, okay, and what this matrix does, A, now in this language, what it does is if the jth interval beats the kth interval, okay, then the new matrix, which I haven't written down, yeah, here it is. So this goes from delta, this takes delta, this composition, Mn plus 1 is Mn times A. What it does is it adds the jth column of Mn to the kth column of Mn plus 1. So you add the jth column of Mn to the kth column of Mn. And that gives you the new matrix Mn plus 1. Okay, so that's just another way of saying what this elementary matrix does. Okay, now what's the goal of all of this? Okay, again, you have choices. And the goal of this, and this procedure goes back, again, at least to Veach, maybe before this following statement. I want to iterate this and get a family, I'm going to get a family of simplices. And of course it's a decreasing, at each stage I'm cutting up my previous simplex into something smaller. So I want to look at the intersection of Mn of delta, n equals 1 to infinity. You do this infinitely often. And what your goal is, you want this infinite intersection in your original picture, you want it to be bigger than a point. So you want the dimension, just the usual Euclidean dimension, you want the dimension of this to be 1 or bigger. So this is an infinite intersection of polygons or simplices, and it's a theorem, certainly, at least of each, that if this is the case, then this infinite intersection is not, the corresponding interval exchange here is not uniquely ergodic, and in fact, this infinite intersection is in bijection with the invariant measures. So Veach says if this holds, then anything in this infinite intersection is not uniquely ergodic. And in fact, again, it's some simplex, and what's true about that simplex is the vertices of the simplex are the ergodic measures. So this is a fairly standard fact. And so the goal is to accomplish this, and in our case, actually the infinite intersections are all going to be line segments. In our case, these infinite intersections will be equal to one-dimensional. Okay? It could be bigger in other cases. Okay, now how do we accomplish that? Okay, so yeah.
In this setting, do you ever get like a pair of simple closed curves? Or is it always?
No, we always get a line segment.
No, I mean,
No, they're.
Is it always minimal?
Yeah, no. I mean, once it's an infinite intersection like this, and if you do Rocha induction infinitely often, you're going to get something minimal at the end. Yeah. If you get a simple closed curve, then Rocha induction will stop at a certain point. Here, Rocha induction goes on forever. Okay. Okay. Now, what's the idea here? Okay, so I want to say two things. One is, again, I've been emphasizing that you always have a choice, okay? But something, if you make, it's often the case, if you make a choice that you want one interval to be bigger than the other, then you're kind of maybe throwing out all of the interval exchanges where the other interval is bigger than, you know, if I want ij to be bigger than ik, great, but I would be maybe throwing out all possible ik's bigger than ij. So at each stage in this construction, we typically have to throw out a set where our limit is not going to lie in that set. Well, okay, one of the things that we have to deal with is make sure, well, I mean, that it sort of has to happen because at the end you have to have measure 0, but you want to not throw out so much that you want to keep enough that you still have positive, this Hausdorff dimension. Okay, so what are these matrices going to look like? So I'm going to draw, this is D equals 6, and I'm going to have a matrix, a 6 by 6 matrix. This is Mn. I don't mean to have a gap here, but these are the first 4 columns, and these are the last 2 columns. Moving closer. Okay, so these are the last 2 columns, and this is the first D minus 2, in this case 4. Okay, so what's going to happen is the first 4 columns are going to projectively converge to the same thing. So the first 4 columns converge to the same limit. So converge to the same limit. Another way of saying it is that the angle between any 2 of the first 4 columns is going to 0. The last 2 columns will converge they will converge to the same thing, but it will be different than what the first 4 columns converge to. So the last 2 columns converge to a different limit. Again, that's our goal. And to achieve that goal, we have to make sure that these columns and these columns make a definite angle with each other. That's another way of saying that. That the columns make definite angle. The D minus first column makes a definite angle, with any of the first D minus 2. And similarly with the D column. Okay, now there's
The last 2 are the same as each other.
the last 2 are the same as each other, yeah. Last 2 is the same. Okay, so that's particular why we get one-dimensional, because these 2 columns will converge to one endpoint of that segment, and the first D minus 2 columns will converge to the other. And it's actually also, this picture is why we talk about the symmetric permutation. The symmetric permutation kind of, for technical reasons, allows a kind of operation that allows us to do this. Now, what do we have to avoid? You see, when we do Rocha induction, we're adding a column to a kth column to a jth column to get the next matrix. Now, here's a simple geometric thing in Euclidean space, which, when you draw the picture, is completely obvious, and but is almost the key to this whole operation. Suppose you have, in Euclidean space, you have a long vector and a short vector. So maybe V1 and V2, and V1 is much longer than V2. And here they're making a 45-degree angle, definitely bounded away from 0. What I don't want to do is add V1 to V2. If you add V1 to V2, then the new V2 prime is almost parallel to V1. Then V2 prime is almost parallel to V1. In other words, I would get a new matrix where now, though maybe this was the D minus first column and this was the first column, and now all of a sudden they started 45 degrees and now all of a sudden they're almost parallel, and we have to avoid that. So we never add a large column of the, when these columns are big and they're much bigger than these, we never add these to these. And conversely, when these columns are much bigger than these, we never add the big columns to the small columns. However, in this picture, if you add a small column to a big column, it doesn't change the angle of the big column very much. A very simple Euclidean geometry. So what that tells us is that we have to be careful about when we build things like this, we never want to add big columns to small columns. And that means in Rauzy induction, whenever, for example, one of the first D minus 2 intervals is in a conflict, it's competing against one of the last two in this Rauzy induction. If one of the first D minus 2 intervals is competing against one of the last two, and they're bigger, then this column size is bigger, then we have to add this column to this, which means that we have to require that the D minus 2 interval is larger than the first two. That's a condition on Rauzy induction when you say one interval has to be bigger than another, and it throws out a set of measure, and you have to control how much you throw out. Now, fortunately, there's a whole, so much of this is probability theory in a way, that we have to control sort of conditional probabilities of what happens if you have a simplex and you're trying to do Rauzy induction, and what is the probability that one of the intervals will be bigger than the other. Now, fortunately, there's a long history of computing these probabilities due to Bill Veach and Steve Kirchhoff. So in a very crucial way, we use their sort of measure theoretic results. So what happens here is that, so let me just try to wave my hands at what we do. So let's say we started off and after a certain stage, and the last two columns are really big. So these are big and small. Small columns. We're at some stage in Rauzy induction. Small columns now have to be added to big ones. They are added among themselves in this Rauzy induction, and every once in a while they might be competing with a big column, but always a small column has to be added to a big column. On the other hand, we want these columns to eventually get bigger than these. So at a certain stage in this Rauzy induction, we have to get to a situation where these columns only compete against themselves. They get added to each other, and the columns get bigger and bigger and bigger until they're eventually bigger than these. So now these columns are bigger than these columns. We move and now start competing with using these intervals. And again, they're smaller than these, so when they fight against these, they always beat them. And we repeat this process over and over again. Big columns, small columns, then you make these big, and so forth. So at each stage, you kind of have to throw out stuff to make this happen. And so let me kind of say that's sort of the idea. And now let me try to, in 5 minutes or 10 minutes, say where the number 1/2 comes from. Why is there a dimension 1/2? Okay. Well, I'll just write this down, and when I'm done, I'll add it. Is it a quarter after 1? Where does 1/2 come from? So that's the, so we have this simplex, and for various technical, I think they're technical reasons, we're going to cut this simplex into a family of parallel planes. So So this is some high-dimensional simplex, but we cut it into parallel, some family of parallel planes. How we get these planes, that's another story. Let's just say that we do. And so here's now, so this was some d-dimensional thing. Now here is the intersection with a plane. So now I'm really drawing something two-dimensional. Okay, so that's the intersection with a plane. Okay, what we're going to prove is that in each plane, well, in a positive dimension set of planes, positive measure, excuse me, positive measure set of planes, so there will be a lot of planes here. There are a lot of planes. Each one of the intersections looks two-dimensional. In a positive set of measure of planes, the Hausdorff dimension in that plane of what we want of the non-uniquely ergodic, in that plane is dimension 3/2. So in each plane, we get dimension 3/2, well, we get actually greater than equal to 3/2. So in each plane, we get greater than equal to 3/2. We lose half a dimension, 1/2 dimension in each plane, but we have a positive measure set of planes, so you lose 1/2 in total. There's a kind of a Fubini's theorem that works here. So why this? Okay, so let me draw a picture of how this is supposed to look. Where does the 3/2 come from? Okay. So here's maybe where we are at stage.
There's a question in the back.
Yeah, oh yes.
In the process, are you always ensuring that you're always unbalanced?
Pardon me?
In the Rauzy induction sequence, are you ensuring that you're always unbalanced?
The matrices?
Yeah.
Yes. Yeah. No, I guess there could be unbalanced, meaning some columns are bigger than.
Yeah.
No, I think maybe there might be a time, very infrequently, when the columns have the same size. The key point is that the angles stay bounded away. So they may be of the same size right now. One group will have to grow, and then the other one is allowed to add to the first. We can't move and change what we do when they have about the same size. Because if they have the same size, if you add one to the other, their angles become too close to each other. So you always have to have columns get big. Along the way, maybe they're the same size, but you don't sort of make big changes when they're the same size.
That's why uniquely ergodic measure of one, right?
Yeah, I mean, they're different. Yeah. I think of it as that you are throwing out a set of definite measure at every stage, and so you throw out full measure at the end. Okay, here's kind of the picture. Here's maybe this is at stage, say, this is maybe at stage K. We have a simplex, and I'll call that the parent. Okay, and then we're going to go to stage K+1, where we're adding some columns to the matrix, and we're going to get lots of children at stage K+1. So these are the children at stage K+1. So what I really mean here, this is mk of delta, and then that's the parent, so that's the big simplex, and each one of these is some mk+1 of delta, each one of the children, for some different mk+1 depending on the child.
Sorry, Howie, so the planes are planes in delta, not planes in the ambient space?
They're planes in delta.
Yeah.
Yeah. So I think the issue is it's hard to work with Hausdorff dimension and high Euclidean dimension. The lines are best. If you're doing subsets of the real line, it's on the face of it easiest to do Hausdorff dimension because covers are easier, because they're intervals. And, well, 2 is better than d minus 1 for us. Okay? And we're able to reduce it to 2 planes. Okay, these are the children. And there are actually exponentially many of them. As K, I mean, I only drew, this parent had 10 children, but actually, in real life, this parent has exponentially many children. And so let me just write down the 2 facts that we have to prove that are kind of the ingredients. So the first fact is, let's say that RK is the diameter of the polygon. Actually, I mean, I've drawn it as kind of a standard polygon, but these polygons are really, at stage K, they're really distorted. I mean, they really look kind of like that. And RK is the diameter. So the first fact is a statement about the decay of diameters. And so the first major thing that we have to achieve is that the diameters don't go to 0 too fast. So we look at the diameter RK of the parent and the diameter of the child. Now this is certainly going to be smaller than that, but if we, for example, for all epsilon positive, the limit of this is 0. So what this says is, I mean, the parent is allowed to, the child is allowed to be much smaller than the parent, but not too super exponentially fast. So not as fast, in other words, it can't go down quadratically at every stage, that kind of thing. It has to be slower than that. So this is like decay of diameters. Okay, and the second major ingredient, so this is the first one. The second major ingredient is to look at the union, the Lebesgue measure of the union of the children. So you look at the children, and you take the two-dimensional Lebesgue of the children, well, the union of the children. So you add up the Lebesgue measures. All these Lebesgue measures are about the same, so you're really multiplying the number, the Lebesgue measure of one by the number. But so that's certainly going to go to 0 because these children will be fairly sparse, but they don't go to 0 too fast. So there's a constant AK. Let me just try to write it down. So this is the parent. Let me write down the parent. So it's at least some multiple of the parent, and what property do these constants have? Well, they're related to the diameter. So if we look at the diameter, now here's the half. If we look at the square root of the diameter, and we look at, if you multiply these AK, so this is the Lebesgue measure of the children compared to the Lebesgue measure of the parent. If you do it again, you'll get the Lebesgue measure of the children compared to the Lebesgue measure of the grandparents, and do it again to the great-grandparents and so forth. So, but this is, the next condition is relating the diameter to the Lebesgue measure, the product of the Lebesgue measures, J equals 1 to K, of these AJ. So the denominator here is essentially the Lebesgue measure of the union of children after K stages compared to the Lebesgue measure of the original simplex. That's what the denominator is. And then we're comparing that to the diameter. So we can think, and the statement is this goes to 0 as K goes to infinity. And we call this a decay of measure. So this is saying, that if you bring this over to this side, this says the product of the measures, the union of the measures is somehow much bigger than the square root of the diameter. And now you put these two facts together and you get the following statement. So all the paper is kind of all about achieving 1 and 2, and you certainly need something about spacing of these children. They don't want to be too close to each other. But essentially 1 and 2 allow you to conclude the following. And then I will stop. There exists a measure mu which is positive on our set. There's some positive measure, call this set A, with the property that if you take any ball of radius r in our simplex, so r we think of as very tiny, that's less than or equal to a constant, well, r squared. So, sorry, no, 3/2. Sorry. No, wait. Sorry. No, yeah, 3/2 is what I want. Not 1, not r squared. Okay, so this says you can build a measure on the set which take for every ball of radius r, the measure of that ball is of the order of r to the 3/2. And now this is the setting of Frossman's lemma, which is a kind of a basic lemma in geometric function theory. So Frossman says that the Hausdorff dimension is greater than or equal to 3/2. Yeah, Hausdorff dimension of so this should be in each plane. Delta intersect the plane. Okay, and that's what we want. So Hausdorff dimension on each plane bounded below by 3/2, so therefore it's greater than or equal to d minus 3/2 overall. Okay, we lose a half a dimension in each plane, and that means we lose a half a dimension total. Okay, I'm finished. Thank you.
Questions for the speaker? Comments? If you fix the dimension of the intersection not to be 1, but any other number that's allowable, would you still guess the dimension?
It's
At least in
yeah, I guess.
D5.
I mean, yeah. So that's a question. It's a good question. If we so let's see. The theorem is that the set of the dimension is at most d over 2, right? Isn't that the best bound? D intervals. Well, G, yeah, but here we're in the interval exchange. It's d over 2, I think. Yeah, thanks. Is d over 2. So, in other words, if you say you want the intersection to be, or you want to build non-uniquely ergodic with 3 ergodic measures, can we also get 1/2? Is that? That's a good question. I don't.
You might have to instead work in a plane to high dimensional stuff.
Could be. We actually asked, this is listed, that question is listed as a question in our paper. Yeah, as an open. Can you do more than lines?
But you get it for D is 5. It's the
Yeah, oh yeah, so it's d over, it's the greatest integer of d over 2. So 5 is 2, yeah, that, well, it's really the genus, but, yeah. It's really the genus, yeah. Yeah, right, that's better than actually d over 2, it's the genus. Yeah, thank you. Yeah. Right. Yes, Alex?
So you said in all known examples, the Hausdorff dimension for NUE x omega is 0 or 1/2.
Yeah.
Might that also be true for divergent directions?
That's a conjecture, a problem. you know, maybe even a finer example, yeah, either 0 or a half. And maybe if it's 0, it has to be very special, like in the Smiley-Weiss theorem, where it's like, it has to be a cover over a beach surf, something like that. That's my feeling. I wouldn't have the slightest idea of how to ever build something that wasn't either 0 or a half. That's not an argument but I have no idea how you ever would get something that was strictly between 0. I know how to build things, sometimes know how to build things with 0 and know how to do a half, but yeah. Yeah.
Yeah, so what is the exact, why does this not work for any other than the ergodic permutations?
Well, because the hyper, so because it turns out, I mean, this hyperelliptic, I'm not saying it doesn't, I mean, we would guess that the dimension is d minus 1 minus a half for every permutation, not just in the Rauzy class of the hyperelliptic. But the hyperelliptic was kind of special because it allowed this sort of decomposition in some sense to the first d minus 2 and then the second 2. And that comes, the way one can kind of think about that is an interval exchange on 2 intervals. It's like a torus, and it's like a d minus 1 surface glued to a torus, and then you're doing, mostly working on the d minus 1 for a long time, and then you switch over to doing stuff on the torus. And I mean, for some, it's, probably the theorem is true in general, but the symmetric permutation allowed for us to get a sort of a nice decomposition of the interval exchange, and frankly, that was hard enough for me anyway. But I would guess it's d minus 3 halves for every permutation. I mean, that's just a guess. Yeah.
Can I rephrase that question as,
Yeah.
What do you need to know about the Rauzy graph for this technology to work?
John? What do we need to know about the Rauzy graph? There's my phrase.
It's used that 3 times, I can explain.
What?
It's used that 3 times, I can explain.
Yeah.
There's some explicit paths that are helpful.
We need
There's
some explicit
application of
yeah.
how twisting is happening near lower strata that's useful, and then there's one just purely technical, convenient thing that probably could be attacked by
So it seems like you have a very good abstract idea of how to do that.
Yeah. No.
If only there's a problem for people to check for other Rauzy graphs.
Sounds great.
Any more questions? No? Then let us thank Howie again.